सचिन पुजेरी, सचिन पुजेरी, अभिनंदन, अभिनंदन, अभिषेक कागवाड़, अभिषेक कागवाड़, अक्षता,
Present, sir.
राइट, आनंद क्याबानी, आनंद, चेतन कुमार,
Present, sir.
सॉरी, वन मिनट, अंजुम बिरादर, अंजुम, बसवराज ऐनापुरे, बसवराज ऐनापुरे, भाग्यश्री, भाग्यश्री, भक्ति,
Present, sir.
राइट, भारती,
Present, sir.
ओके, चेतन कुमार,
Present, sir.
राइट, दीपक,
Present, sir.
राइट, दिव्या, दिव्या, गढ़ प्रथमेश शिवाजी, गढ़ प्रथमेश शिवाजी, ज्योति, ज्योति, किरण लिगाड़े, किरण लिगाड़े, लक्ष्मीकांत, लक्ष्मीकांत, मानतेश,
Present, sir.
राइट, मोळे प्रेम,
Present, sir.
ओके, नागेश, नागेश, नंदीश,
Present, sir.
राइट, पूजा पाटिल,
Present, sir.
ओके, प्रमोद कुमार, प्रमोद कुमार, प्रवीण मखदुम, प्रवीण मखदुम, प्रियंका,
Present,
प्रियंका,
sir.
ओके, संध्या, संध्या, संतोष पुजारी,
Present, sir.
राइट, संतोष सोनार, संतोष सोनार, शाहबाज,
Present, sir.
ओके, शफिया,
Present, sir.
राइट, श्रीधर, श्रीधर सोलकणवर, सृष्टि,
Present, sir.
ओके, सिद्धार्थ,
Present, sir.
राइट, सिद्धार्थ पाटिल, सिद्धार्थ पाटिल, सुप्रिया,
Present, sir.
ओके, वंदना,
Present, sir.
ओके, वसंत दोडमनी,
Yes, sir.
राइट, वेददत्ता, वेददत्ता, योगेश, योगेश, महेश दोडमनी,
Yes, sir.
राइट, बाळेश, बाळेश, तैक मोहम्मद, तैक मोहम्मद, प्रवीण राठोड,
Yes, sir.
ओके, अभिषेक पालेकर, अभिषेक,
Sir.
राइट,
Present.
ओके, ऐश्वर्या,
Present, sir.
ओके, अमानुल्ला, अमानुल्ला, बंडुरकर तनय मोहनदास,
Present, sir.
राइट, भावराव, भावराव, शोधन,
Present, sir.
ओके, द्यावण्णवर अनिल कुमार शेकप्पा,
Present, sir.
राइट, Nandkumar. Nandkumar. Pramod Kesti. Pramod Kesti. Rohini.
Present, sir.
Okay. Rohit Alwani. Rohit Alwani. Shashidhar Gaudar. Shashidhar. Sridhar Badiger.
Present, sir.
Right. Saish.
Present.
Saish.
Present,
Snehal.
sir.
Okay. Snehal. Snehal. Vaishnavi. Vaishnavi.
Present, sir.
Okay. Karthik Yam.
Yes, sir.
Okay. Smita Melgiri.
Present, sir.
Right. Okay. In the last class, the discussion was on the instructions, right? We'll continue with those instructions. Are you able to see the screen here?
Yes, sir.
Yes, sir.
Okay. Thank you. Next instruction is JMP at A plus DPTR. JMP at A plus DPTR. The name itself will indicate that it is a jump instruction. Jump at that particular address or jump to that particular target address. Syntax of this instruction is JMP at A plus DPTR. JMP at A plus DPTR. This instruction transfers the program execution to the target address which is specified in the instruction. That is, the target address is mentioned in the instruction. To that particular address, it will jump. This is unconditional jump instruction. That is, without any condition being satisfied, it will jump to the target address. That is, it is called as unconditional jump instruction. Description of this instruction is: this instruction transfers the program execution to the required target address. Target address is provided by adding the value in A register with the value in DPTR register. Jump at A plus DPTR means the value in A register is added with the value in DPTR register, and that will give the target address. For example, let us say the value in A register is say 03H. Value in DPTR is say 2004. A plus DPTR, this value will be P plus 2004, it will be 2007H. It will be 2007H memory location. At A plus DPTR, this means it is at the memory location 2007H. At 2007H. That means the jump will take place to the memory location 2007. To this memory location, the jump will take place. Right? This is how this instruction will execute, and it will jump to the required target address. Operation of this instruction is indicated by the value in A register is added with the value in DPTR register, and that will be stored in the program counter. The program counter will jump to the address which is obtained by adding the value in A register with the value in DPTR register, which is nothing but the target address. None of the flags are affected when this instruction gets executed. No flags are affected. Next, conditional jump instructions. Conditional jump instruction. Now, just which all instructions we have gone through, they are unconditional jump instructions. Next, which all we will be studying, they are all conditional jump instructions. Conditional jump instructions are the instructions which perform the jump operation after the condition is being satisfied. After the condition satisfies, only then it will jump to the target address. Such instructions are called as conditional jump instructions. The first one among conditional jump instructions is jump if 0 or jump on 0. Correct? It is 2 machine cycle instruction and it takes 2 bytes. It is a 2-byte instruction and it takes 2 machine cycles to execute. Syntax of this instruction is JZ target. That is, if the value in accumulator is 0, only then it will jump to the target address. When it will jump to the target address, only if the value in A register is nothing but the accumulator. If the value in accumulator is 0, only then it will jump to the target address. That is why it is a conditional jump instruction, because the condition is if the value in A register is 0, then perform the jump to the required target address or to the specified address. Right? It is conditional jump instruction. Function of this instruction is transfers program execution to the required target address if the value in A register is 0 or if the value in accumulator is 0. This is 2-byte instruction. It is 2-byte instruction. The first byte is for the opcode. The second byte is for the target address. The target address is 8 bits, so it is 2 raised to 8 means 256 byte. The jump can take place anywhere within the 256 byte memory location from the program counter. It is 2-byte instruction. It is having 256 byte range of the jump, right? 256 byte of the range of the jump instruction. What is meant by 256 bytes? 256 byte means here minus 128 byte. If it is a reverse jump, if it is a jump in the backward direction, it is minus 128 bytes. If it is jump in the forward direction, then it is plus 127 bytes. Right? The total from minus 128 to plus 127. Right? It will be 256 bytes. Clear here? If it is in the backward direction, if the jump is in the backward direction, then it is backward jump is minus 128 bytes. If it is in the forward direction, then it is plus 127 bytes from the memory location of the program counter. Clear here? We have studied what is a backward jump, what is forward jump. Just here we are mentioning that it is minus 128 bytes in the backward direction. If it is backward jump, then if it is in the forward direction, forward jump, then it is plus 127 bytes from that value of the program counter. The operation is indicated by PC plus 2. That is the value in program counter, whatever is there, to that value plus 2 we have to do, because it is 2-byte instruction. That address will be stored in program counter. To this address, that is the address of the next instruction after the JZ instruction, that instruction address, that instruction, next instruction, memory location, wherever it is stored, that memory location plus the relative address. Okay. For example, if the instruction is stored, say, in 2004 memory location, JZ instruction, it is stored in 2004, right? Then in 2006, the next some other instruction is stored in 2006, because JZ is 2-byte instruction. It is stored in 2004, the opcode is stored, and in 2005, the relative address is stored. And in 2006, the memory, it is the memory location where the next instruction is stored. Some instruction is stored in 2006 memory location. 2006 plus the relative address. 2006 plus the relative address. The relative address is, say, 03. In 2004, JZ instruction opcode is stored. Say, let us say it is as, say, for example, in 2004, it is the opcode of JZ instruction is stored. Let us say it is at 97 is the opcode for JZ, okay, JZ target address, JZ target address. Next you can use, or JZ back you can use, whatever it is, target address. In 2005 memory location, the relative address is stored. Let us say the relative address is 03. Okay. Then in next 2006 memory location, the opcode of some other instruction is stored. Let us say I'm using the instruction, let us say move. I'm using the move instruction, move a comma hash 23h. This instruction I'm using. The opcode of this instruction, let us say it is 1 byte instruction. Okay, it is 2 byte instruction because 1 byte is for the opcode, another byte is for the value here 23h. This is stored in say next memory location 2006. Its opcode, let us say it is 54h is the opcode for move a comma hash 23h. Right? I'm just giving an example. Then in 2007, the second byte is stored, that is the value, this value 23h. It is stored in 2007, 23h. Now, this JZ target address, how the target address is calculated here? Program counter will be storing the address of the next instruction. Address of the next instruction after JZ is move a comma hash 23h. Its memory location is 2006. Is not. Therefore, program counter will be storing 2006. This memory location, which is there in program counter, to this what will be added? Relative address will be added. What is the relative address? The second byte. Second byte has the relative address. This memory location plus 03. This will be 2009. Therefore, the target address is 2009. I gave the example in one of the classes about J and Z next. Right? I wrote a program and I explained how J and Z next, how the next address is calculated, or how the target address is calculated. What is the memory location of that next? That is a target address. So 2006 plus 3. The next is somewhere else. Right? There's some other instruction is stored in 2009, which is the target address for the JZ instruction. Right? This is how it will calculate the target address. PC plus relative address will be stored in the program counter. None of the flags are affected when this JZ instruction is executed. Similarly, we have JNZ. JNZ is just opposite to that of the JZ instruction. JZ is jump if the value in A register is 0. JNZ is if the value in A register is not 0, only then it will jump to the target address. Just opposite to that of the JZ instruction. Syntax is JNZ target. JNZ target. Function of this instruction is transfers the program execution to the required target address if the accumulator value is not 0. The accumulator value is not 0, only then it will jump to the required address. Description is target address is again within 256 bytes of the value of the program counter. That means minus 128 byte in the backward direction. Okay, and then plus 127 byte in the forward direction. Backward direction means the instructions which are before the J and Z instruction, or the instructions which are before the JZ instruction. And other instructions which are after the JZ instruction, they come under forward jump. They come under forward jump. Operation is the program counter value is added with the value 2 because it is 2 byte instruction, 1 byte for the opcode and the second byte for the relative address. That will be stored in program counter, and only if the value in A is not 0, then it will add the value in program counter, that is the address of the next instruction, plus the relative address that will give the value of the target address, which will be stored in program counter, and it will start executing the instructions from the instruction which is stored at that particular target address. Again, none of the flags are affected when this J and Z instruction gets executed. Are you following here, students? Did you follow this JZ instruction, J and Z instruction? Is it clear here, these instructions? Okay. Next, CJNE instruction. Compare and jump if not equal. Compare and jump if not equal. Syntax is CJNE destination byte comma source byte comma target address. What this instruction will do is it will compare the value in destination with the value in source. If the two values are not equal, if the values are not equal, only then it will jump to the target address. What is the instruction? CGNE destination byte comma source byte comma target. This is syntax, right? General format of the instruction. Then it will compare the value in destination with the value in source. If the two values are not equal, only then it will jump to the target address. The function is transfers program execution to a specified target address if the magnitude of the source byte and destination byte are not found to be equal. They should not be equal, only then it will jump to the target address. If they are equal, the question is, if they are equal, then what will happen? If the value in destination byte destination is same as the value in source, that is, they are equal, then it will not jump to the target address. Then what it will do? It will execute the next instruction immediately next to the CJNE instruction, right? It will continue the program execution from the instruction very next to the CJNE instruction. From that instruction, it will continue and it will end the program. That is, description is, this instruction first compares the magnitudes of the source and destination bytes. If they are not found to be equal, if they are not equal, only then it will jump to the target address given by the third byte of the instruction. This is 3-byte instruction. CGN is 3-byte instruction, right? That means it takes 3 memory locations. To store the CGN instruction, it requires 3 memory locations. One for the source, that is one for the opcode, and the remaining 2 bytes is for the target address. If they are equal, continues with the next instruction following the CJNE instruction. CJNE jumps only for the not equal value. Compare and jump, if not equal, jumps only for the not equal value. To find out which is greater, right? Whether destination is greater or source is greater. To find out how can we check it, whether destination is greater or source is greater. Is there any method to check that? Can anybody suggest me any method to check whether destination is greater or source is greater? How to check it? How to verify? Can you think on it? I want to check whether the value in destination is greater than the value in source, or whether the value in destination is less than the value in source, or the value in destination is same as the value in source. That is, they are equal. How to check it? How to check that? Which flag we have to check in order to find out whether the value in destination is greater or less or equal to the value in source? Which flag we have to check? Yes. Which flag we have to check here? Akshata? Which flag we have to check here?
Yes.
Which one? How many flags are there? How many flags are there in 8051 microcontroller? 4 flags: carry flag, auxiliary carry flag, parity flag, and overflow flag. Is it not? Now, among these 4 flags, which
Yes,
flag, if we check, we'll come to know whether it is greater or less or equal. Okay, let me explain that. See here, if we want to check whether destination is greater than source or equal or less than, we have to check the carry flag. If the destination is greater than, or if it is equal to the source, right, then the carry will be 0. Remember, if the destination is, if the value in destination is greater than the value in source, or it is equal to the value in source, then the carry will be 0. Then when will be the carry equal to 1? The carry will be equal to 1 if the destination byte is less than the value in source. If the destination value is less than the value in source, and the carry will be set. Okay, the carry will be set if the destination is less than the value in source. Like this, we will come to know by checking the carry flag whether the value in destination, whether this value, left side value, is greater than the source, or it is equal to the value in source, or it is less than the value in the source by checking the carry flag. It's clear here.
Yes, sir.
Okay, fine. Next, if they are equal, then it will continue with the next instruction immediately after the CJNE instruction. Suppose if they are not equal, only then it will jump to the target address. When it will not be equal, when carry flag is 1. When carry flag is 1, it indicates that the destination value is not equal to the source value. Only then it will jump to the target address. Now, in case if the two values are equal, if the value in destination is equal to the value in source, then it will not jump to the target address. It will continue the program execution from the instruction next to the CJNE instruction. From the instruction next to the CJNE instruction, whatever instruction is there, from that instruction, you will continue the program execution till the end of the program. Till the end of the program, right? CJNE jumps only for the not equal value. It will jump only for the not equal value to find out if it is greater or less. After the comparison, CY flag must be checked or the carry flag must be checked. Okay. So if this flag is checked, then we'll be understanding whether it is greater or less or equal to the source value. Which are the various instructions of CJNE then? The various CJNE instructions are like this. CJNE A comma direct comma relative address. Which addressing mode is this? CJNE A comma direct comma relative address. Which addressing mode is this? Yes. Which is this addressing mode? Will tell me. Yes. Bhakti. Which addressing mode is this? CJNE A comma direct comma relative address. Bhakti. Can you think on it? Bharti? Bharti? So direct addressing mode, because we are using direct here, direct memory location we are using. CJNE A comma direct comma relative address. Memory location we are using, is it not? Therefore, it is direct addressing mode. Direct means it is a memory location. Yes or no? Therefore, the value in E register is compared with the value in memory location. If they are not equal, the two values are not equal, only then it will jump to the target address. There is 3-byte instruction. It takes 2 machine cycles to execute. What is the instruction? CJNE A comma direct comma relative address. CJNE A comma direct comma relative address or target address. Both are one and the same. Right? Here, value in A, let us say value in A is 04. And direct, let us take the memory location as this memory location. Let us take it as say 58H. Okay, 58H. Right? In 58H memory location, in 58H memory location, let us store the value. Say 05. Now we'll compare the value in A register with the value in memory location 58. The two values, are they equal here? No, they are not equal. Value in A is 4, value in 58H memory location is 5. They are not equal. If the value in these two are not equal, only then it will jump to the target address. Of course, here value in A is 4, value in 58H is 5. They are not equal. It will jump to the target address. Well, this condition is satisfied. Is it not? Condition is satisfied. A value is 4, 58H memory location value is 5. 4 and 5. It will compare. Value are not equal. These two are not equal. By checking the carry flag, it will perform Cy is equal to 1 because it will perform the subtraction here. 4 minus 5 is the carry will be set or the borrow will be set. Therefore, carry will be 1. 4 minus 5 subtraction operation it will perform. As the carry is 1, it will find out that the two values are not equal and then it will jump to the target address. Clear here? This is how it is jumping to the target address. Did you follow here how it will jump to the target address? It is 3-byte instruction and it takes 2 machine cycles to execute. Next, CJNE A comma hash data comma relative address. The same as that of A comma direct. In direct A comma direct, we are storing the value in memory location. This is immediate addressing mode. This is immediate addressing mode because hash symbol is used, and we are using directly the value in the instruction. We are using immediately the value in the instruction. Hence, it is immediate addressing mode. Hash symbol is used. It is immediate addressing mode. In this immediate addressing mode, the value in A register is compared with the value here. This hash data, this value is compared. If the two values are not equal, only then it will jump to the relative address, or only then it will jump to the target address. Next, CJNE RN comma hash data comma relative address. To compare the value in this RN register, N may be any value between 0 to 7. It can be R0 or R1 or R2 or R3 or R4 or R5, any register up till R7. The value in that register is compared with the value here, immediate value. And if the two values are not equal, only then it will jump to the target address. Right? This is register addressing mode because here register is used. RN is a register, correct? RN is a register. As register is used, even though hash symbol is used here, register is used here. Therefore, it is register addressing mode. If A comma hash data is used, then it is immediate addressing mode. If some register is used like R0 or R2 or R5 or R7, then it becomes a register addressing mode. CJNE at RI comma hash data comma relative address. Which addressing mode is this?
Indirect.
Indirect addressing mode. Very good. It is indirect addressing mode because at symbol is used. At symbol is used because of that is indirect addressing mode. In indirect addressing mode, we know that suppose if you are considering R0, I may be 0 or 1. It may be R0 register or it may be R1 register. Maybe R0 register or it may be R1 register. Value in R0 register is a memory location. In that memory location, some value is stored. The value in memory location in R0 or R1 register is compared with the value, this hash data, it is compared with hash data. If the two values are not equal, only then it will jump to this relative address. Right? Value in memory location in register R0 or R1 is compared with the immediate, is compared with the value here, the hash data value. If the two values are not equal, only then it will jump to the relative address. Only then it will jump to this target address. This is CJNE instructions. Any doubts up till here? Any questions up till here? Everybody, are you following here? Any questions, any doubts up till here? Yes, any questions up till here? Chetan, any doubts? Chetan, Deepak, any questions here up till now? What all we discussed? Deepak, Mantesh?
No, sir, no.
No doubts? Following, right?
Yes, sir.
Okay. Next instruction is DJNZ, decrement and jump if not 0. DJNZ instruction. Syntax of this instruction is DJNZ byte comma target. DJNZ byte comma target. Decrement and jump if not 0. Full form of this instruction is decrement and jump if not 0. CJNE full form is compare and jump if not equal. DJNZ instruction full form is decrement and jump if not 0. The name itself will tell you what is the function of that instruction. DJNZ instruction function is, it will decrement this value, whatever this byte value is there, it will decrement to that. After decrementing, if the value is not 0, only then it will jump to the target address. Transfers program execution to the specified target address if the value of the byte specified is not 0 after it is decremented. After decrementing, if the value is 0, suppose if the value is 0 after decrementing, after subtracting 1 from this particular value, if the value is 0, then what it will do? If the value is not 0, only then it will jump to the target address. Suppose if the value is 0 after subtracting 1 from this byte value, then it will not jump to a target address. It will start executing the instructions immediately from the next instruction after the DJNZ instruction. And the program execution continues with the next instruction after the DJNZ instruction. Again, here the target address is 256 bytes. It is 2-byte instruction. It is having 256 memory locations from the current program counter memory locations. That is the range of the DJNZ instruction. You will have to remember the ranges. In few of the question papers, they have asked what are the ranges of the different jump instructions. Right? You have to write the syntax and then you have to explain the ranges. What is the range of DJNZ? What is the range of CJNE? What is the range of JZ? Right? What is the range of SJMP instruction? Short jump instruction, LJMP, long jump. Right? All those jump instructions you have to explain their ranges. None of the flags are affected when this DJNZ instruction gets executed. Some of the instructions of DJNZ are DJNZ RN comma relative address. It is 2-byte instruction and it takes 2 machine cycles to execute. RN, it may be any register between R0 to R7. Value in this R0 to R7 register is compared with this relative address. If the two values are not equal, right? Sorry, if it will decrement the value in RN register. After decrementing, if the value is not 0, only then it will jump to the relative address. Only then it will jump to this target address. Similarly here, DJNZ direct comma relative address, it is direct addressing mode. The value in memory location is decremented by 1. Okay, let us say this direct memory location is 40H. In 40H memory location, let us say the value stored is 5. 5 minus 1 it will perform. It will perform 5 minus 1, subtract 1 from the value. After subtracting, after decrementing the value, if the value is not 0, after decrementing, if the value is not 0, only then it will jump to the target address. Only then it will jump to the target address. Clear here? This is DJNZ direct comma relative address. If the value is 1, then what will happen? 1 minus 1 is 0. 1 minus 1 is 0. If it is 0, it will not jump to the target address. It will not jump to this relative address. Instead of that, it will execute the next instruction after the DJNZ instruction in that program. This is 3-byte instruction and takes 2 machine cycles to execute. I had given a homework program for you all to write it. Write an ELP to find the sum of 20 bytes stored in an array of external RAM starting with address 2000H. Store the 16-bit sum at the end of array. Have you all written this program here? Anybody tried this program? Anybody tried out this program here? You have to write an assembly program, assembly language program. ELP means assembly language program, to find the addition. Sum means addition of 20 bytes stored in where these 20 bytes are stored. Starting from in the array they are stored, right? In which array? What is the starting memory location of that array? External RAM memory location. External RAM it is. So whenever they are using the word external, you have to use which register? DPTR register. DPTR register should be used. Starting with the address 2000H. Store the 16-bit sum. Store the result at the end of the array. At the end of the array, that is, how many values are there here? 20 bytes are there. 20 bytes stored in the array. That means in 2000, first byte is stored. In 2001, second byte is stored. In 2002, third byte is stored. Like that, in 2019 H memory location, 20th byte is stored. In 2019 H memory location, 20th byte, 20th value is stored. After that 2019 memory location, whatever answer you are getting, the addition of all these values, 20 values, whatever sum you are getting or whatever answer you are getting, that answer you have to store in 2020 H memory location, that is the higher byte, and in 2021 H memory location, the lower byte of the answer, lower byte of the answer. Like that, you have to perform the addition. Let us go through that program here. Program, it is similar to the program that we have written in the previous class, and that is write an ELP to add n 8-bit numbers available from memory location start, display the result on port 0 and port 1. It is almost similar. Few instructions are different. I'll just write down that program here. Let us take starting memory location as 0000H, 0000H, starting memory location. As we have 20 values, I will initialize the count, move R0, I am storing the count in R0. You can take any registers, need not be only R0. Move R0 comma hash 20, move R0 comma hash 20, right? Then starting memory location is given. This is all the initialization part. Move dptr, comma hash 2000H, 2000H, starting memory location. As they have mentioned, external memory location, and it is, they are using 20 values, right? They are given 20 values, and it is external memory location. Address also they have given 2000H. It is 16-bit address. Therefore, you have to use dptr register only. Next, what will be the next instruction here? We have initialized the count. We have initialized the starting memory location. Next, we have to initialize where to store the higher byte and lower byte of the answer. I'm storing in R1. I'm initializing it. Move R1 comma hash 00H. Then move R2. I'm storing the higher byte of the answer in R2. R2 comma hash 00H. This is the same. All this is same. Whatever we discussed on the program, that is ELP to add n 8-bit numbers, starting from memory location START. That program you just see. Then we have the loop. It's also same, back, using the loop here that we can write later. Back, move x a comma at dptr. I'm getting the first value stored in 2000H. I'm moving it into A register. I'm moving it into A register. Right? Once I move it into A register, then I will add this value, whatever I have in A register, with the value in R1. Because in R1 I am storing least significant digit. I'll write it here. I'm storing least significant digit, LSD. And in R2 I am storing the most significant digit or the higher byte. Okay, most significant digit or the higher byte. X a comma at dptr. Then I will add the value in dptr. Now dptr first memory location is 2000. At 2000, whatever value is stored, that will be moved into A register. That value I am adding at first value, it is add a comma r1. A comma r1, because lower significant digit is stored in r1. I am adding that value with a first value in dptr, that is first value in 2000H. Okay, so after I add, what I will do is will move the result right into r1 again. Move r1 comma a. Move r1 comma a. I am moving it into r1 because next time when I want to add, I will take the second value into A register, then I will add it with the previous sum. Previous sum is where? Now my previous sum is in R1 register. Previous sum is in R1 register, right? Because I am moving the sum which is in A into R1. Therefore, when I want the next addition to perform, what I will do? I will take the second value, I will increment DPTR, I will get 2001. Whatever the second value, that I will move it into A register. Then I will add it with R1. Then I will add it with R1. The result, whatever I am getting, sum. Right? This is as good as you perform, right? Sum is equal to sum plus A of I in your C language. You have an array of numbers. First you initialize sum as 0. Then you perform sum is equal to sum plus A of I. You are adding the array of numbers, correct? It is similar to that. Move R1 comma A, move R1 comma A. Then after this, what we are supposed to do, we have to add with carry. If there is any carry generated, that also we have to consider. That is stored in R2 here. R2 comma hash 00 H. What this will do? R2 is equal to R2 plus 00 plus carry Right? Is there any carry generated? It will check from the previous edition. Previous edition is 0 plus first value in 2000. If there is no carry, then this answer will also be 0. R2 will be 0, because initially we have taken R2 as 00 plus 00 plus carry. If the carry is 1, R2 will be 1. If carry is 0, then R2 will also be 0. Is it not? Next instruction, after ADDC R2, we have to go to the next memory location, increment DPTR, right? Then how to check the loop condition here? Which instruction I have to use to check the loop condition? Can anybody tell me how to check the loop condition? Which instruction I have to use?
DJNZ.
DJNZ, exactly. DJNZ R0, R0 I have taken, count is in R0, comma back. This is the loop, right? Once it performs the addition of all the 20 numbers, all the 20 bytes, which is stored starting from memory location 2000H. Once it adds all these numbers, then next what they are saying, just look at the statement. Store the 16-bit sum at the end of the array. That is, in 2020H and 2021H memory locations, you have to store the 16-bit answer, whatever you are getting after adding all the 20 values, after adding all the 20 bytes. To perform that, what I will do is, I will move the value in R2. R2 is having the most significant digit, that is a carry, most significant digit. I will move it into DPTR. First, I have to get the next memory location. To get the next memory location, I have to move the value. Already here incrementing process has taken place. Increment DPTR. Again, I need not increment. Okay. So after it has moved all the 20 values, the next memory location will be 2020. So what I will do? Move X, move A comma R2, move A comma R2. The value in R2 is the most significant digit, that I will store in A register. Then move X at DPTR, comma A. This instruction I will use, so that the value in A register will be stored in the 2020H memory location, which is now in the DPTR register. It is the end of the array. Then I have to store the least significant digit. R2 is most significant digit. This is for the most significant digit, MSD, most significant digit. Correct? Now I have to store the least significant digit. To store the least significant digit, what I have to do? Again, I have to move the value in R1. R1 has the least significant digit. R1 has the least significant digit. Add A comma R1 we are doing every time, right? We are adding the equation, that is sum is equal to sum plus A of I, that equation, right? We are storing every time in adding, and we are storing in R1, correct? That value I am moving in A, move A comma R1. Then to get the next memory location, I have to get the next memory location here. So I have to increment DPTR first, INC DPTR, then move A comma R1, then move X at DPTR comma A, move X at DPTR comma A. MOVX at DPTR comma A. That means in 2021 H memory location, how I am getting the 2021? Increment DPTR. DPTR will be 2020 plus 1. 2021. Then I am moving the R1 value, that is sum of all the 20 numbers, least significant byte, LST. That I am storing in A. I am moving from R1 to A. And from A register, I am moving it into 2021H memory location. This is how I am moving it. And once it is done, I will exit the program using the instruction SJMP $, SJMP $, and then I will end the program. I will end the program. All these instructions are same. I have already explained these instructions and I was explaining that program on ALP to add n 8-bit numbers available from memory location start. Up till here it is same. Only the next part, right? So from here to here it is same. All these instructions. This is all same. What I explained in the previous class. Okay. Only the next portion after this, that is these few instructions, end of the array, how you are storing the value, that is only different here. Okay, so you all understood here how to store the result at the end of the array. You have already incremented here DPTR. It is after you are storing, adding all the 20 values, the increment DPTR means it will be pointing to 2020H memory location. DPTR will be storing 2020H memory location. Move A comma R2. R2 is nothing but the sum of all the values. That is the most significant digit, most significant byte. That value I am moving it in A. Then from A I am moving it into DPTR memory location. DPTR memory location is 2020. I want the next memory location. If I want the next memory location, I have to increment DPTR. It will be 2020 plus 1, 2021. Then move A comma R1. R1 is having the least significant digit. R1 is having the least significant digit or the carry. That I am storing in A. From A I am storing it into 2021H memory location. I have stored my result, that is the most significant digit and the least significant digit. Both of them I have stored. Then I will exit the program. Short jump $ and end. Right? Is this program understood here to everyone? Is this program understood here to everyone? Clear here? This program? This program is clear here? Yes? Nandish, is it clear here? Nandish?
Yes, sir. Yes, sir.
Okay. Mole Prem? Mole Prem?
Yes, sir. Understood, sir.
Understood. Okay. Sandhya Shirodkar? Is it understood? Supriya? Supriya, is it understood?
Yes, sir. Understood. Yes, sir.
Okay. Fine. Aishwarya?
Yes, sir.
Clear? Is it clear? Program and today's instructions are clear?
Yes, sir. Yes, sir.
Any problem in understanding?
No, sir.
Okay. Shodhan?
Yes, sir.
Understood? Shodhan?
Yes, sir. Understood, sir.
Okay. Vaishnavi, is it clear here? Vaishnavi Sanikop? Vaishnavi? Smita Meligeri? Smita? Understood? Sridhar Badiger? Sridhar?
Yes, sir. Understood, sir.
Clear with the today's topics?
Yes, sir. Yes, sir.
Okay, fine. Then we'll wind up the today's class here. In the next class, we'll continue with the next instructions. That is, few more jump instructions are remaining. No operation instruction. Few more instructions are remaining. We'll take up those instructions and then any programs then we'll take up in the next class. Okay. Thank you.